Alrighty, banked roads and curves. Understanding the physics behind racetracks and highways. Why do racetracks and highways have banked turns? We will look at several situations involving roads that have banked and non-banked turns. A flat road plus straight track, a flat road plus circular track, a banked road plus straight track, and a banked road plus circular track. We are going to see how the driver and the car act on each type of scenario. Flat road plus straight track. Gravity pulls the car down while the track pushes the car up with an equal and opposite normal force. While the car moves straight ahead, there is no sideways force, so there is no sideways friction force. Flat road plus curved track. The car drives at speed v around a circular track with a radius of r. Centripetal force is pushing the car toward the center of the track. There is a friction force between the road and the tires, so the friction force has a maximum magnitude. The car will stay on the track as long as the force of friction is equal to force centripetal. Banked road plus straight track. The road is tilted at angle theta and runs in a straight line. Gravity pulls down and has two different components: into the road and along the road. Along the road, the car is pulled sideways. In order to prevent it from sliding to the left, there must be a force of friction. Force of friction must be greater than or equal to the force of gravity parallel. Banked road plus straight track continued. The friction force depends on the normal force. The normal force is exactly the same as the gravity into the road. In order to keep the car from sliding to the left, mu must be greater than tangent theta. Banked road plus curved track. A track is banked at angle theta and runs in a circle with a radius of r. Two forces must be considered: gravity and the normal force from the road. The force of gravity is equal to mass times the acceleration of gravity. To keep the car from falling through, the road has to push straight up with an equal and opposite force. Banked road plus curved track continued. The car is now moving in a uniform circular motion, so there is a force pushing against it. The normal force can provide the centripetal force. We want to build the track right that can provide the right amount of force so the cars can move in a uniform circular motion. So, banked road plus curved track continued. So, to keep the car from falling through the road, force normal must equal mass times the acceleration of gravity divided by cosine theta, and to keep the car in a circular motion, force normal must equal mass times speed squared divided by radius sine theta. And to keep the car moving in a circular path and from falling to the road, tangent theta must equal speed squared divided by gravity times radius. Summary plus overview. Track banking is important because it ensures safe driving around an oval track at high speeds, 200 miles per hour plus. Most banked tracks have a slight banking on the straightaways and a maximum banking up to 36 degrees in the turns, so the car can carry their speed through the turns without flying off the track. High banking can contribute to accidents if the car is going too fast and smashes into the safety barrier, but most of the time it's because of lack of grip and downforce going into the turn along with going too fast. Some tracks don't have banking like road courses and circuits, which means you can't go as fast through the turn, unlike an oval track or speedway. We're excited. Thanks for watching.